So this is the reason behind the third parameter. You get extra information. You got location, you still got your ordered pair, your location, and you've got what time it is. That's cool. When you get to Calc 3 and you do calculus all over again in 3 dimensions, you'll actually have parametric equations for 3D. And so you'll be working in 3D. And so you'll have 3 parametric equations instead of 2. You'll have an X and a Y and a Z. And you'll have some funky curve, whatever. And it'll also have some orientation. So there'll be an arrow indicating, what direction the motion is happening. And you'll have a time T that says what time it is at that moment. So if I picked a point right here in 3D, I would have an ordered triple. I'd have the location given by X, Y, and Z coordinates, but I also have exactly what time it is when the object is passing through that point P. And that makes all the difference. Okay, now we're going to do calculus. So what about it? Well, once you have your curve, let's say right here at this point P, I wanted to draw a tangent line there. And I even wanted the equation of the tangent line. Yeah, okay. Well, I definitely need to, if I'm going to have an equation of a line, get the slope, right? Isn't that what we need for lines? Sure. So you're going to get the slope of the curve, or your tangent line to the curve, by learning this cool parametric form of the derivative. And so here it is. And you want to put this on your cheat sheet for the final. This stuff is not going to be on the midterm. Don't worry. This week's material will not be on the midterm Monday, okay? This stuff is going to be on the final. dy dx, that's the slope of your tangent line, can be found by taking the derivative of the y parametric equation with respect to t and dividing that by the x. And of course, this works as long as the denominator isn't equal to 0, because you don't want to divide by 0. So that's why they have this little extra here. Dx dt not equal to 0. Yeah, okay, fine. So let's do an easy example. We're going to find the slope of the curve at a time and then at a point. And so, this is the 2 different flavors that you'll be given on the homeworks as well as quiz 12, which is going to have, I forgot to mention, there will be a quiz before your final. I'm going to make it pretty easy though. I think I'm going to make it where you don't have to give me any handwritten work. Just do it. Okay. So how do you get the slope? So the slope dy dx, if you use the formula, is dy dt over dx dt. Please don't do this upside down. The biggest mistake I see students do, and I give you 0 points if you do this, is they accidentally, I know when you take a test or a quiz, you're like scared. They accidentally put the dx dt in the numerator and the dy dt in the denominator, and they do this back asswards, and then all hell breaks loose because I don't give you any points for that. Why not? Can't you give me some mercy points? No, because you've got your cheat sheet right in front of you. Put a little note to yourself, note to self, don't do this upside down so you don't screw up. So dy dt, here's the y, it's 3t minus 5. The derivative of 3t minus 5 is 3. And then divide that by the derivative of t squared, and that's 2t. And boom, there's your slope with regards to t. So if they want to evaluate this at t equals 2, no problem, just substitute. So 3 over 2 times 2 is 3/4, and there's your final answer for letter A. Done. Is it that easy? Yes. Well, that's easier than power series. Yeah, I know. This is a nice break. We're finishing up the semester with stuff that's easier. Great. Now, what about if they want the slope at the 0.94? Now, this one's tricky. Why is it tricky? Because they're not giving you the time. And I hope you notice that this slope that we got, you need the time t in order to figure out your slope. So here, they're just giving you a location. So as I mentioned at the beginning of the lecture today, when you have a point, there's always 3 pieces of information that go with the point: the location, the x and y coordinates, and the time t. And sometimes it's tricky. If you have one, you got to get the other. So here they're just giving you the x and the y. So here's what I do know: x is equal to t squared. So if 9 is equal to t squared, and once I square root both sides, I get t is equal to plus or minus square root of 9. T is plus or minus 3, but you have to pick one of those, and you can't guess. So how do I get which one, plus or minus? Hang on, I'm getting there. The y parametric equation, they told us, was 3t minus 5. And they're telling us that y is 4. So that you replace your y with a 4. And then solve this for t. Add 5 to both sides and then divide both sides by 3. And so this tells me that t has to be positive 3 in order to match the location of the point. So here where we were confused, should it be plus or minus? The time has to be the same for both x and y. So it turns out that t is equal to 3. And that will give us the location 9, 4. Fantastic. And then substitute this into dy dx. So dy dx evaluated at t equals 3 would be 3 over 2 times 3, which is 3, 6, which is reduces to a half. And that's the final answer for letter B. A little bit harder because you kind of had to do some work to get the time that correspond to that location. Does that make sense?
Yes.
Always t squared.
They told you what the parametric equations are up here. X is equal to t squared.
Okay.
See, this is given. And so, and they should give you the parametric equations for you so you can do the job. Okay. So we'll keep going. Now, what about the second derivative? I'm not as interested in the second derivative, and I give very few problems like this on tests. But it turns out, and this is really weird, because when you're getting the second derivative, which gives you access to the kind of concavity that's happening, is it concave up or concave down? You basically take the derivative again of your first derivative, and this is what's really weird, is it's this formula. You take the derivative ddt of your dy dx, which you got already. You got it from up here, this, okay? So you stick that there and take the derivative of that with respect to time t, and then you divide by dx dt. What? Yeah, weird. So we're going to use that for example 2. So what is d squared y over dx squared for us? That's what they want to know. I don't know. Well, you're going to take the derivative with respect to time of the dy dx, which you already got in example 1, and divide it by dx dt, which you also got in example 1. So what they're saying is you want to take the derivative with respect to time of this first derivative we got, which is 3 over 2t. We'll do that in a minute. And you're going to divide that by whatever dx dt was originally. Well, remember that x, they gave it, was t squared. So the derivative of t squared is what?
2t.
2t. So that's what goes in the denominator. And now we still have to figure out the numerator. If I were you, I'd rewrite this as 3/2 t to the -1. And that way you can take the derivative using the power rule. So you still have the 3/2, -1 times t to the -2. This 2t just stays in self. Clean this up because I don't like all these yucky complex fractions. This is going to be -3 over 2 times 2t times t to the +2. And then when you clean this up, I get -3 over 4t cubed. That's the concavity. Okay, and so that'll tell you if it's concave up or concave down at a particular time. Okay, now the proof of this second derivative, if anybody's interested, come visit me in office hours. You need the chain rule to go do it. It's more like the chain rule from calculus 3 though. That's why I kind of don't like to do it here. Okay, all right, so we're done with that. So now let's just do a couple more examples that are a little bit tougher, and then we'll finish with finding the equation. Oh, we got to do equation of a tangent line and horizontal vertical tangencies. Okay, yeah, all right, gotcha. All right, so let's do that. So here's an example. It's a little tougher to go get the derivative, first derivative and second derivatives. Okay, fine. So they're giving you the parametric equations, and you certainly could graph these. I mean, heck, you know, if you're like, well, I want to know what the graph looks like. Okay, fine. Then bring up your graphing calculator and clear out whatever garbage you had from last time. And let's see, this sine squared, so I guess I need parentheses, sine t squared is the first equation. And oh, I blew it. Let me go back. I didn't want to square the argument. I wanted to square like that. Okay, that looks better. Okay, and then cos t, boom. And let's see what my range of t is. Ooh, that's way too much. Boy, that's overkill. Negative 12 to 18, I don't think so. Let's just do 0 to 2 pi. That's usually the typical, but not always. All right, let's see what we get with this beast. If I hit graph, let's see what the orientation is. Oh, my goodness. Let me zoom in on that. It's kind of tiny. Okay. It looks like the right half of a circle. Interesting. Now, that makes me think, well, what if I changed the T maximum to 4 pi? Would I get more of the picture? I don't know. Let's check it out. Nope, it goes back over on itself. So it looks like it went down and it went back over on itself. So it's only that right half of a circle, and it's oriented back and forth. That's kind of a cool example. I like it. So in other words, what would this look like? It looks like I'd have to put one arrow in one direction, and then when we have more time, it actually backs over on itself over and over again. Just that right part of a circle only. That's an awesome looking curve. I like it. Okay, so now what? Well, they didn't ask us to graph it. I just did that for a quick break. Okay, so, now, like if I were going to, come up with the equation of a tangent line at some point, it would be nice to get the slope, which is dy dx. But dy dx for parametric looks like this. First take dy dt and divide that by dx dt. Okay, fine. So dy dt is easy. The derivative of cos, I believe, is negative sine. Okay, fine. Now the derivative of x with respect to t, if I treat this sine squared as sine t squared, you'll go 2 sine t using the chain rule, and the derivative of sine t is cos. Okay, now I'll just leave it like that because now I can reduce to lowest terms, and this looks like negative 1 over 2 cos. If you wanted to rewrite this as negative a half secant, that's fine also. They're equivalent, right? How would I get the second derivative? Well, I would take the derivative of the first derivative and then divide that by dx dt. Now remember, I already got dx dt when I was doing the first derivative, so I don't want to reinvent the wheel. I'm just going to copy that down. Heck. And then does anybody remember from our work with trig, what the heck is the derivative of secant? This is good review for the final, people. It's secant tangent. Yeah. It's the product of secant t tangent t. Oh, yeah. Now, you could go, well, this is the final answer. But it turns out, if you want, to look a little bit more sweet here, well, this 2, you can bring it down. So you have negative 1 over 4. Secant is 1 over cos. Tangent is sine over cos. And then you've got sine cos. Does any of this help? It looks like it's just getting worse. Well, this cos, you can bring it down and then combine it with this cos down here, and same here. So it looks like if I clean this up a little bit, I'm going to have 3 cosines, and then the sines can cancel. So it's like, okay, they're gone. So I have negative 1 over 4 cos t cubed, and if you wanted to convert to secants, you could write it like this, secant cubed. Okay, so there's the second derivative of that guy. And we're done. So nothing to it. This is basic calculus stuff, but not hard, okay? Taking derivatives. Okay, now find the slope, the equation of the tangent line, and describe the concavity. Oh my God. I don't feel like doing all this. I'm too tired. I'll tell you what. Let's get the slope and the equation of the tangent line. Let's do that. That's kind of key. Concavity, don't care. Okay, I don't care today. You can go get it. If you're really interested, I'll tell you what the answer is. And but I think the equation of the tangent line is classic. So First up, if I'm going to get the equation of the tangent line, I need the slope of the tangent line. So what is it? Well, slope is dy dx. But the parametric form is dy dt divided by dx dt. Well, what's x and y? Well, they gave it to us right here. There's your parametric equations. And if you want, you can go graph it just for fun, take a break, and see what the curve looks like if you like. Fine. So then what? Well, if I take dy dt, derivative of t cubed is 3t squared. Divide that by dx dt, I get 2t minus 1. I'm done. But what do I want to evaluate it at? T equals 2. So if I evaluate at t equals 2, this is just substituting. So I have 3 times 2 squared all over 2 times 2 minus 1. Okay. What do I get? 12 over 3, but that reduces to 4. Okay, save that for later. Now what? So when you do the equation of a line, I hope I'm just going to do some basic algebra here. It looks like this. You guys seen this point slope form? One of my personal favorites. So the 4 is going to be the slope. Good. But then what's x1 and y1? Give me a point on the line. Well, they gave you parametric equations and they told you t equals 2. So the x1 is just the x coordinate at t equals 2. And so you'll just plug 2 into your parametric equation for x, and you'll get t squared minus t. So that's 2 squared minus 2, but I get 2. And then the y coordinate, which is going to be the y1 in our line equation, is found by just substituting the time into the y parametric equation, and that's t cubed. So that's going to be 2 cubed, and I think that's going to be 8. So the point that we're trying to get the tangent line to is at the point 2, 8. So then what? Well, now you're ready for this equation. Y minus y1, okay, y minus the y coordinate, which is 8, is equal to the slope 4 times parentheses x minus the x coordinate. Okay, and you're pretty much done, although a lot of times they like you to clean up the line equation and maybe write it as, mx plus b. So I would, clean up a little bit here. All right, fine. Oh, shoot, man, if you add 8 to both sides, I get y equals 4x. And that's nice. And we're done. So I just got the equation of the tangent line. So if you did go to your graphing calculator for kicks and giggles here, and you graph this set of parametric equations to get the curve, and then we'll look at the point that they're asking us to find this tangent line to. So let's see, the x parametric equation was t squared minus t, and then the y was t cubed. And I like to see the full picture. So for the window here, I'm going to go from -10 to a t max of +10 seconds, just to capture everything. And then when I hit graph, remember it's going to have, whoa, holy smokes, what just happened there? Let me do a zoom out. That was weird. Oh man, that's pretty cool. I like it. Do you notice that there's a point where it looks like there might be some weird sharp corner? And I imagine that happens when the denominator of the derivative is 0. It's probably got some weird sharp corner or cusp there at t equals 1/2, which would have the location, what would be 1/2 squared 1/4 minus 1, -3/4 1/2, I think is where it kind of does something really funky. But I think the place where they wanted us to find the tangent line is the point 2, 8, which is like somewhere up here. And so we just got the equation for that tangent line for a point way up here. So that's kind of cool. All right, so we're done with example 4. We got an equation of a tangent line. Any questions so far? Okay, so this is a classic thing to ask you, is like, hey, when is the curve going to have any vertical or horizontal tangents? And that just means if you drew a tangent line to it, would you get a horizontal tangent line, which has a slope of 0, and a vertical tangent line, which has a slope of what? Does anybody know what the slope of a vertical line is? I'm waiting.
0, 0.
Okay, that would be the slope of a horizontal line. So what's the slope of a vertical line?
Infinity?
Yeah, yeah, undefined usually.
Oh.
They say undefined. Yeah, you could say infinity, but usually people say it's undefined because it's so steep you can't measure it, right? So everybody remember that? Horizontal tangents have a slope of 0. And vertical tangents have a slope of undefined.
Yes.
Does this ring a bell from an algebra class, or are you guys too dead to care at this point? You too dead to care? Yeah. I hope not, because we're still here. You know, I always like to tell my students, you know when it's time to take a nap and like go all, I want to go back to bed? After the final's over, people. Otherwise, you're still here in the class. It's still going. And unless you want to take Calc 2 again, you want to like finish out in success, let's focus up. Okay, so how do you get these horizontal and vertical tangents? Well, sometimes what I like to do is I like to graph it and kind of get a look-see first, like, ooh, what am I looking at? And it turns out if you whip out your graphing calculator in parametric mode, and you're like, oh, I want to see this, your x is 2 minus 3 cos theta. So they're using theta as the parameter. No big deal. We don't care. We're going to still use t. And the y parametric equation is 3 plus 2 sine theta, but I'm just going to, oh, shoot, I forgot to do a clear. Sorry. Let me clear that crap out. Sorry. 3 plus 2 sine t. And then I'm going to look at my window. I think negative 10 to 10 is overkill. Let's go from a 0 to 2 pi. I think that might be enough to see the full picture. And then when I hit graph, check it out. Woo! Oh my goodness, that is a cute little ellipse that's not centered at the origin. Fine. Can you guys see where the horizontal tangencies would be? Like if you drew a tangent line to this ellipse, where you would get a horizontal? Can you see like right there at that point, if I draw a line, that's horizontal? And how about down here? Horizontal tangents? There's 2 of them. Cool. What else? Well, I claim there's a couple vertical tangents too. Look right there. I draw a tangent line. Well, that's vertical. How about over here on the other side of the ellipse? Well, that's vertical. So if I do this problem correctly, I should find 2 horizontal tangencies and 2 vertical tangencies, and then I'll be done if I'm really doing this the way it should be done. So that's the plan. So if I go back to here on locations, you got a little ellipse there. So I first have to go get dy dx, okay? And it's dy dt, although here the parameter they're using is theta. I don't really care. Theta, t, whatever they're using, fine. So dy d theta over dx d theta. So dy d theta is going to be 2 cos. And dx d theta is going to be, the derivative of cos is minus sign, but then you already have a minus there. So minus minus is going to be a plus. Okay, so like that. All right. So I could rewrite it as cotangent, but I don't want to. Leave it. So when am I going to have a horizontal tangency? That's when dy dx is equal to 0. When is a quotient equal to 0? When the numerator is equal to 0. So when is 2 cos equal to 0? And you guys should know, divide both sides by 2 to get rid of the 2. And then take arc cos of both sides. And you better be good at doing this. I know this is trig. What is cos inverse of 0? You can use your graphing calculator, but it'll only give you one answer.
Pi over 2.
Pi over 2. Good. Are there any other locations that we have that who have angles whose cosine value?
Negative pi over 2.
Negative pi over 2, right? Which is the same as 3 pi halves, right? Same, whichever one. So let's stay with that. So those are the horizontal 2 spots now on 0 to 2 pi, which is what I care about. Now, folks, that doesn't give me where it is. That just gives me what time it is, like what it's pi half seconds when we have one of those horizontal tangencies, and it's 3 pi half seconds when we have the other. So what are the actual locations, the x and y coordinates? So you go back to your parametric equations, like for the x, and you plug in, you know, x evaluated at pi halves here, okay? And cos of pi halves is 0. So one of the spots here will have an x coordinate of 2. And then if you look at the y parametric equation and you plug in pi halves, I think sine of pi halves is 1. So you get 3 plus 2 times 1. I get 5. So this point is 2, 5. That's going to be one of the spots, one of the locations on your curve that will have a horizontal tangent line. Now, if you go back to the picture that we drew of this ellipse, does that make sense to you? Do you see the 0.25 is up here? Right there?
Yes.
This pen sucks. Anyway, that's the point where we got a horizontal line. So there's another spot too, because, and we looked at the curve, so we kind of know there better be 2. So if you go back to your thing and you evaluate x at 3 pi halves, and then I'm just going to do this really quick because it seems like a lot of you don't care. I get x is equal to 2 again, and then y evaluated at 3 pi halves, blah, blah, blah. I think I get a 1. So the 0.21 will be another location that we have a horizontal tangent line. Fine. So we're done with horizontals. Now let's do verticals. So, well, how do you get vertical? Well, if you look at your derivative, knowing what we know about vertical lines, we want the dy dx to be undefined. So how do we get this to be undefined? Well, that will happen when the denominator is equal to 0. That's the key right there. So look at the denominator. It's 3 sine theta. When is that equal to 0? So first divide both sides by 3, and then take arc sine of both sides. And then what's angles that you know of that have a sine value of 0? On 0 to 2 pi. Let's just look at that interval only.
2 pi. I mean pi and 2 pi.
Yeah. 0, which is the same as 2 pi, and pi, right? And that just gives you what time it is. It doesn't give you the locations. So the actual locations are where you're going to substitute this parameter, which happens to be theta, into your x. So you'll get 2 minus 3 cos of 0 will be one of the x coordinate locations. I think cos of 0 is not 0, it's 1. So this is 2 minus 3 times 1. I get negative 1. And then the y evaluated at 0 is 3 plus 2 sine 0. And that's just going to be 3. So the point negative 1, 3 is going to be one of the spots we're going to have a vertical tangent line. Does that look true to you on the curve? Yeah, it does. I mean, if you look at the point with coordinates right there, negative 3, 1, that will have a vertical tangent line. I believe it. I believe it. And then you get the other one by plugging in pi. So x of pi, you'll end up with x is equal to 5. And then y evaluated at pi, you'll end up with y is equal to 3. So the location with coordinates 5, 3 will be another location on your curve that has a vertical tangency. Pretty cool beans, huh?
Yeah.
So that is classic kind of crap that you do with parametric. Okay, fine. Now let's do the second half of today's wonderful lecture. The other big deal, and you're going to see this in 3D and in Calc 3, okay? This parametric stuff you're going to see in Calc 3. Same with the arc length. So I already taught you arc length for functions of x. So let's just do the review. So this is review here. The formula was S is equal to the integral going from A to B. And the weird radical was square root of 1 plus y prime getting squared dx. So we did this way back, I think in either the first or second week of school. Fine. So what has this got to do with us? Like, how are we going to get the length of a curve in parametric? I mean, any curve, you know, we could do on that ellipse that we saw over here. Like, let's say I wanted to find the length of the curve between time t equals 0 and t equals, I don't know. I'm just making something up, you know, 2 pi thirds or something. That would be interesting to find out. So what's the parametric version of arc length? So that's what we're gunning for right now, the parametric version for arc length. So let me do the derivation because it's kind of cool and it's not that hard for you guys to understand. Plus, you kind of need this to do some of the problems anyways. So you start with what you know, and then we plug in place of y prime, the dy dx for us, because that's what y prime is. But remember, the parametric dy dx is dy dt divided by dx dt. Really? Yeah. So your integral is going to look horrible. Like, good luck with that. Like, is it even going to be integrable? I don't know. You're going to take this and square it and divide by this thing and square it. Yikes, that's horrible. Because that's your y prime getting squared and then dx. It's like, ugh. What if that's not integrable? Yeah, what if it isn't? So the next step that you're going to do is you're going to rewrite the 1 so that he's still a 1, but let's give him the common denominator of dx dt squared. So 1 is equal to dx over dt squared divided by dx over dt squared. And then when both of those terms underneath the radical have the same denominator, good news, you can combine them in a one big old quotient, which is like, oh, this looks even more horrible. I don't even think this was a good idea. Yeah. It's like, oh, why did we do this? This is horrible. Now I'm going to do another trick. I claim that dx can be replaced with an equivalent. It's the same as dx dt times dt. Well, why can I do that? Because you can think of these dt's as almost canceling. Which they don't, but just do it. So I'm going to replace that. And then what? Well, then I'm running out of room. The next step is just algebra. We're going to go, hey, you know when you take the radical of a quotient like we have here, I'm going to rewrite that as a quotient of radicals. So I'm going to have the square root of whatever the numerator is divided by the square root of the denominator. Oh man, and over here I still have dx dt times dt. So I'm going to have the denominator and then the numerator square root, which is still looking pretty horrible. But then, good news, this here is going to just simplify to dx dt, which is awesome because something magical happens. This dx dt cancels that dx dt. And then, so then what? So this is gone. And so what's the only thing you have left? This radical right here. And folks, that is your final answer. So in this box over here, here's what I want you to put. Arc length, which is little s in all math books, is the integral going from a to b, the square root of dx dt squared plus dy dt squared dt. Now, I have a true-false question for you. Is this, so true or false, is it legal to rewrite this integral as the square root of the first term plus the square root of the second term and then simplify some more? Yes or no?
No.
No, that is called illegal math. If I catch anybody in this class doing it, I'm going to reach through the internet and virtually wring your neck. Okay? Please don't do that. That's illegal math. All right? Not permitted ever. Ever. Okay? So don't do it. Now, the other little caveat here is that you're only allowed to use this formula on smooth curves. Like if it's got a cusp or a sharp corner anywhere on your interval, you might get some weird answers like 0 and you'll get all pissed off. So be careful that you choose an interval that doesn't contain any sharp corners or cusps. Okay? Also, you don't want to have your curves sketched out more than once. So like you were finding arc length of a circle and you wanted the whole arc length like 0 to 2 pi. Don't do your a to b 0 to 7 pi because you'll get an answer that's way too large and it's not the actual arc length. Okay, that would be bad. Okay, now I got a couple examples for you. And I know I'm just talking at you and that's how it is. And I apologize for that. But we're jammed for time and we're trying to wrap this semester up because I don't want to be lecturing like over the weekend before the final. Like, forget that. I got to finish it. And next week is polar. Parametric isn't so bad. polar can be weird because you're learning a new coordinate system. I love polar and you need it for calculus 3 big time. So we're going to do some exciting stuff next week. All right, so let's do find the length of a curve. All right. Real quick, I want to say, you know, when you're finding the square root of something squared, do you guys remember this is absolute value of x? Do you recall this little handy fact? Yes or no?
Yep.
Yeah.
That's true. And well, when can you strip off the absolute value bars? Well, if you know it's positive on a certain interval, you can strip it. Like, did you guys do this in Calc 1? Like, let's say you had y equals absolute value of x. And they go, hey, here's the graph of y equals absolute value of x. Hey, find the integral between -1 and +2. Were you allowed to do this? No, you were not. Because I don't know about you. I have no idea how to integrate an absolute value. I just don't. Period. It's not possible. Don't go, well, I did it in Calc 1. No, you didn't. Here's what you did. You notice that this diagonal line has the equation y equals -x. And then over here, after, you know, where the vertex was 0, so you're going to have to split this into two integrals, one from -1 to 0, and then 0 to 2. The one from -1 to 0, you'll actually integrate something that doesn't have absolute value in it, -x. And the one on the right-hand side has the positive slope, so it's positive y equals +x, and then you would add the results. Okay, and that's how you would do an integration of an absolute value. This is important that you know this. If you didn't learn that all the way in Calc 1, I just filled in some gaps for you, okay? This is going to become a little important because this problem is a little bit weird, okay? And it needs this sort of handy fact for you to get. Okay, so now what? Okay, go get the length of this curve, and the interval is time going from -1 to 0. Fine. So what do we know? The arc length is going to be the integral going from -1 to 0 of the square root of x prime of t squared plus y prime of t squared. Okay, fine. So what is x prime of t? Well, look at x. They gave it to you. It's t squared plus 1. So what's his derivative?
2t.
2t. So you're going to go, okay, 2t squared plus, and then what's y prime? If y is equal to 4t cubed plus 3, what's the derivative of that?
12t squared.
12t squared. Now go integrate that. Now that looks horrible. Like, oh my God, am I going to have to use trig sub? Please tell me no. Good news, no. But you have to do some algebra cleanup before you're able to do the actual integration for this puppy. And then you'll end up using the power rule. So watch closely how I do. Right now, this is actually a Calc 1 problem. It's a hard Calc 1 problem, but I would give it to my Calc 1 students. And that's why they hate me. Okay, so clean it up. Oh, shoot, man. So what 2t squared is going to be what? 4t squared? Okay, and then what does 12t squared end up being?
144t to the 4th.
Man, this looks really bad. Don't use u sub now. Oh, I can use u. No, you can't. Here's what I'm going to do. I'm going to factor out the GCF, the greatest common factor. What is common between 4t squared and 144t to the 4th?
4t squared.
4t squared.
Yeah, I think 4t squared. And then what would my other factor be? It'd be 1 plus, you know, whip out the calculator. I think it's 36t squared, like that. Okay, still not integrable. But then you're going to use the law of radicals that says, hey, and when I have a product underneath a radical, and that's what these two things are doing with each other, it's a product, you can take the product of the factors. Now, this is where that recall comes into place. This right here is 2 times the absolute value of t, okay? This is what you're trying to integrate. And I don't know how to integrate absolute value, period. I don't. I have a master's degree, don't help me. But here's the thing. If you looked at that absolute value of x, a graph that I did up here, which is the same as absolute value of t, notice on the interval -1 to 0, on this interval, -1 to 0, t is this absolute value of t is really negative t. So that's what you replace him with. Really? Yeah. So you're really going to negative t square root of 1 plus 36t squared. Okay. And you're going like here. And if the 2 and the negative bother you, then just pull it out of the integral. You're like, okay, that bothers me. All right, fine. So then just pull it. It's just a constant multiple anyway. So, you know, if it's giving you an annoyance there, move it out. Now what? Power rule, baby, with u sub. Power rule. Yay. Let u be what's under the radical, 1 plus 36t squared. The derivative of 1 plus 36t squared, I believe, is 72t. And then we have the dt. Good news. I already have a t and a dt in the integrand. I just wish I had a 72, but that's not a problem because you can always make your wishes come true by putting a 72 in there, provided you divide it out. That's like multiplying by a special version of 1. And now this looks like negative 1/36, the integral of square root of u du. But that's negative 1/36, the integral of u to the half. And then using the power rule on that, negative 1/36, 2/3 u to the 3/2, and then put your u back in there. And after I reduce this to lowest terms, because 2 divided by 36 is 18, 1/18. So I'm going to have 18 times 3, I believe, is 54. And then I'm going to have 1 plus 36t squared to the 3/2. Woo! And I'm evaluating that on this interval, negative 1 to 0. Good God, man. Okay. And I get negative 1/54th. And then when I first plug in the 0, all right, like that. And then minus, and then I plug in the negative 1. Well, that's going to get squared, so that'll make him positive anyways. Okay. And then what the heck? So this is just going to be 1 minus 37 to the 3/2 multiplied by negative 1/54th. And the good news, this is a positive number, and it better be, because if you get a negative number for arc length, oh my goodness, that can't happen. Better get a positive number, otherwise something went wrong. Okay, questions? I know we did a lot here, but it's just arc length. Now, folks, do you remember arc length from day one? Like, you know, am I being crazy here?
I have a question, Professor.
Okay, go. Yes.
So you said the answer on the arc length it will never be negative,
Correct.
so it's always positive, though.
Yes, sir.
Okay, thank you.
If you get a negative number, you may check your work.
Okay, thank you.
Check your work. Something happened, man. It's not pretty. Okay, so here's a nice blast from the past for you, for those of you who are still with me, okay? Do you remember back in section 6.5 when we did arc length? Here's some of your old lecture notes. Oh, did we really do that? Yeah, we did. You were there. Told you about a Van Koch snowflake that has infinity arc length. Yeah, there is such a thing. So just to let you know, John, you won't get infinity. Here was the definition of arc length. Can't have any sharp corners. And I did some examples. This is just review. That example was terrible. I wouldn't read that one. That one sucked. It was just trying to prove that you would get the distance formula if you use straight line. So this one was kind of hard because you ended up having to clean up your radicand, because do you remember that it would factor as a perfect square sometimes? Not always, but sometimes. Remember some of those? I put a couple of those on the quizzes, remember?
Yeah.
If you don't, read it. And then this one right here, example 4 was easy. This was just an easy power rule one right here. You know, square root of u du. Kind of looks like the one we just did. So just to let you know, these arc length ones, they always end up having, you know, a weird radical in them because it's arc length. And arc length involves a weird radical, whether you're doing the f of x, you know, y equals f of x regular arc length formula, or you're doing the parametric version of arc length that we are doing, which is right in the middle of. That's when you're going to use this formula here. I'm going to just roll back to it right here. Oops, right. Come on, baby. Right here. This arc length version, the parametric version. Okay. Know it. Okay, I think I'm going to do one more problem and then I'm going to call it a day. And you guys can go off and, you know, study for your midterm or get ready for Thanksgiving. I'm going to go have a 2-hour office hour. You're welcome to come. Let's just do example 7 here and we'll wrap it up. Okay. So you'll see this one in your homeworks because it's a classic. Like every single calculus book has this one in it. I'm not making this up, people. Look on my wall here. You see all these calculus books I have? Yeah, they all have this problem in there. Okay, so you should see it and know it and be enlightened. Here we go. Find the length of the curve from 0 to pi halves. Now, I'll tell you a funny story about this before I do this problem. One time I was doing a quiz, and this problem shows up in Calc 3 also. And I was making a quiz and I said, oh, okay, find the arc length of this curve on 0 to 2 pi. And I like to make solution keys for my quizzes before I actually give them to my students. And thank God I did that because of the fact that, oh, here's something fun. I haven't shown you this thing, but okay. So this is one of my favorite graphing tools that I use a lot in Calc 3 because I can graph in parametric as well as polar, which is really cool. So I'll graph this in this parametric. Let's just do this. Okay. So cos t. Oh, bummer. Let's see if I can cube it. Cubed. Ah, there we go. And then down here, what was it? Sine of t cubed. I wonder if I could do this. Sine. Let's just see if it lets me do it. Cubed. No, it doesn't like it. Never mind. Oh, no, don't get rid of the whole thing. Please don't do that. Okay, so I got to do this. Sine t cubed. Okay, there we go. Now let me just hit it. Oh, it's only giving me a part. Oh, bummer. I hate that. Let's see what my parameters. Okay. Oh, here we go. So I want my x to be, okay, let's just do this. Sorry. It gets a little grouchy. Let's see if this will do it. Let's see if it'll work now. There we go. Okay, see this diamond shape here, folks? Can you see that okay? Let me switch it over here for you.
Yeah.
So do you see that there's 4 cusps on this diamond? Say yes. Well, when I was doing my solution key for this quiz for my students, I said, hey, find the arc length of this entire diamond, using these parametric equations. Well, it kept coming out to 0. And I'm like, damn it. Why do I? And I kept redoing the calculation like, oh, maybe I'm just tired today. It turns out I was totally screwing up because the arc length formula doesn't work if your interval has sharp corners like this one. So how would I find the arc length of the entire diamond? Well, use symmetry. Find it from 0 to pi halves, which just gives you this one little piece, and then just use symmetry, multiply by 4, and that'll give you the entire diamond. That's how you're supposed to do it. Okay, silly me. Even teachers make silly mistakes, okay? And hopefully that won't be you trying to do your arc length formula when there's a sharp corner or a cusp. Okay, let's get dx dt first because it's going to require the chain rule here, so it's going to be a little dicey. If I think of this as being cos t, the quantity cubed, and using the chain rule, I'll have 3 cos t, the quantity squared, times what's the derivative of cos?
Negative sign.
Mm-hmm. Okay. dy dt is going to be 3 sine t, the quantity squared, times cos. Okay. So now you're ready to set up your arc length. So your arc length little s is going to be 0 to pi halves. you're going to have a nasty square root, and then you'll have dt over here. So you're going to have this 3 cos squared t, and I'm going to not put the negative because I'm going to square everything, so it's going to end up going to a positive, plus 3 sine squared t cos t squared. Okay. Oh my God, that looks terrible. How are we going to integrate that? Don't worry, it's all going to come out in the wash. Okay. So what is this radicand going to have in it? I'm going to get 3 squared, which is 9, cos to the 4th power sine squared for the first term, and then I'll get 9 sine to the 4th power cos squared for the second term. And this even looks more horrible. It's like, oh my God, I can't integrate that. That's terrible. So the next step is find the GCF of these two terms, similar to the last problem. Anybody see it? What's common to
9.
both? 9 is a good start. Anything else common to both?
Cosine squared
Mm-hmm.
and sine squared.
Mm-hmm. And then what's the other factor going to be after you pull out that GCF?
Cosine squared.
Mm-hmm.
Would that just be it?
No, plus.
1?
No,
Sine squared t.
sine squared. And then this adds up to 1, doesn't it? By a trig identity. Does everybody see what I'm doing here?
Yes.
I'm not even integrating yet. We're not there yet. We're not there yet. So now it's like, oh, I got to integrate this whatever's left here. But don't even do that. You're going to use the fact that this square root of 9 is 3. And then the square root of something squared is you get these absolute value bars thrown in there. But good news, cosine and sine are both positive on 0 to pi halves. So since both cos t and sine t are positive on the interval 0 to pi halves, you can just strip off the absolute value bars and not worry about it. And then just keep going. Yeah, Zeke, I got you. I know you're there, Twinkies. I love you too. Come here. Come here. Okay. So what you're going to do is you're just going to integrate 3 cos t sine t. And I'm just going to use the power rule. I'm going to let u be sine t. Du is just cos. Hey, good news. This just looks like, I'll pull the 3 out, 3u du. And then when you integrate that, you get 3u squared over 2, but that's 3 sine squared t over 2, and you're evaluating between 0 and pi halves. Do you see why if I evaluated between 0 and 2 pi, I'd get 0? And I kept screwing up. Yeah, that was hilarious. Okay, and then you'll go, okay, what's sine squared of pi halves minus sine squared of 0? Well, sine of 0 is 0, so that's gone. But what's sine of pi halves?
0?
No, sine of pi halves.
No, 1.
1.
Pi halves is 1. So this is 1 squared, but that's just 1. So final answer is 3 halves. So the little diamond shape that I showed you there, one of the little sides there is 3 halves. So if you wanted the arc length of the whole entire diamond, you'd have to multiply by 4, and you get 4 times 3 halves, which would be 6. So the entire diamond's arc length all the way around the diamond would be 6 units. Pretty cool, huh? And yes, you got to get a positive answer because arc length is positive. Okay, and that concludes today's lecture. Congratulations, you're almost done with the semester, people. Don't give up. We're getting really close. Have a happy holiday.
Could you scroll to the past